In this video, I'll go over the basics of the valence shell electron pair repulsion model. We can use this approach to predict the shape of a molecule based on the electrons that repel each other in the atom. The electron domains that will repel each other in this model will be made up of either shared or lone pair electrons. The shared electrons are shared between atoms, and lone pair electrons exist when there's no bond being formed with those electrons, but they are surrounding an atom nonetheless. But they are around an atom nevertheless. The most stable arrangement that a molecule will find will be the one with the least repulsion between these electron domains. The domains will want to be as far apart as possible, but still being connected to the central atom. And we'll see examples of this shortly. A summary of electron and molecular geometries is below. Some of the types we'll encounter will be linear, trigonal planar, and tetrahedral. A linear model is in the shape of a line. This is a picture of the trigonal planar molecule. This is a bent molecule. And this one is a three-dimensional tetrahedral molecule. And there's other shapes shown here as well. Let's try to predict the shape of a BeH2 molecule. And we want to say, what is the angle between the bonds of this molecule? Now, sometimes it can be difficult to tell which atom is going to be the central atom. In this case, it's not difficult to tell. Hydrogen can't be a central atom because it can only bond to one thing. So instead, Be is going to be the central atom. We can also see that in the table of electronegativities below. And electronegativity tells us how strongly an element attracts electrons. The table shows that fluorine is the element that attracts electrons the most. If we look at beryllium, Be, its electronegativity is 1.5, but we see that hydrogen's electronegativity is 2.1. Now, it's usually the case that the element with the lowest electronegativity is the central atom. And in this case, beryllium actually does have a lower electronegativity than hydrogen. Hydrogen's an exception to the rule, though. As we'll see, even though hydrogen has a lower electronegativity than fluorine, for example, hydrogen cannot be a central atom. So it's an exception to the rule. But anyway, here the rule actually holds. Beryllium does have a lower electronegativity than hydrogen, so it'll definitely be the central atom here. Let's draw it. Beryllium brings 2 valence electrons to the table here, and hydrogen will bring 1 each. Alright, that's the start of our Lewis dot structure. Now let's just bond the beryllium to the 2 hydrogens. Now what we see here is that 2 bonds are formed and there are no lone pairs for beryllium. So the number of electron domains that this molecule has is going to be 2. You always want to think about what's around the center atom and how many electron domains is it attached to. In this case, it's 2 electron domains. And there's nothing else. There's no other lone pairs. There's no other bonds. So the type of molecule that this is going to form is going to be a linear molecule. We see that there are 2 electron domains we've got two bonded groups and no lone pairs. The angle between the bonds is going to be 180 degrees. In mathematics, that is called a straight angle. And what they're talking about is the angle between the right side here of the beryllium and the left side. That's going to be 180 degrees. So this is a linear molecule. Go ahead and draw the carbon dioxide molecule for yourself using a Lewis dot structure and see what kind of shape this molecule might have. Okay, let's check out the electronegativity of carbon and oxygen. Carbon has an electronegativity of 2.5. Oxygen has an electronegativity of 3.5. The element with the lower electronegativity is typically going to be the central atom. So let's let carbon be the central atom here. So we'll have C. Now the carbon will bring 4 electrons to the table here. The oxygens will bring 6 each. Now in order to satisfy the octet rule, carbon is going to form 2 bonds with each oxygen here. This way carbon will be bonded to 4 plus 4 is 8 total electrons, and each oxygen will also be in contact with 8 electrons. So everyone's happy. And now when we go to see how many bonded groups we have, let's see. So we have yet again 2 electron domains. We can have more than one bond in a domain. So this is, even though it's a double bond, it's still going to be considered one domain there. And there's one domain on the left of the carbon. That's 2 total domains. Those domains want to repel each other. And so the idea is the electrons don't want to be near each other, and the domains will try to stay as far away from each other as possible. That will make an angle of 180 degrees. We have 2 bonded groups, no lone pairs. So this is going to be another linear molecule. It was the example given in the table, actually. Let's draw an HCN molecule. Go ahead and draw an HCN molecule and decide what shape the molecule might take. Alright, so between hydrogen, carbon, and nitrogen, if you look at the table of electronegativities, hydrogen has the lowest electronegativity of all of them. Hydrogen with 2.1, carbon with 2.5, and nitrogen with 3. But hydrogen can't be a central atom, so we believe that carbon here would be the central atom. Let's draw it. Nitrogen brings 5 valence electrons to the table. Carbon brings 4, but it only needs 1 to bond with the hydrogen over here. And so, since nitrogen needs to bond with 3 electrons, this would be the setup. And now the octet rule is satisfied for carbon and nitrogen. Hydrogen, of course, only needs to satisfy the duet rule, where it's in contact with 2 electrons. Now, what type of molecule will this make? Will it make a bent shape, or would it be linear? it actually ends up being linear like the others. Even a triple bond could be one electron domain. And the angle between these two domains will be 180. All right, that's 3 examples of linear molecules. Now let's try to draw a BCl3 molecule. Boron clearly has the lowest electronegativity between itself and chlorine, so it can be the central atom. Boron also brings 3 valence electrons to the table. So let's draw that. Each chlorine only needs 1 electron to bond with because it already brings 7 to the table. This is the structure of BCl3. And now let's go to the table here. We've got 3 electron domains. When we have 3 electron domains and 3 separate bonded groups and no lone pairs, then we have the trigonal planar molecule. The domains want to stay as far away from each other as possible, and since it does reside in a plane there, 120 degrees would be the ideal angle for them to stay away from each other. So what they mean by planar is, if you just look at a plane of a piece of paper, for example, all the atoms are going to be in that 2-dimensional plane. And so there won't be any like above the paper, and there won't be any below the paper. They'll all be on the paper. And so this is what the molecule could look like if it were perhaps on the plane of a piece of paper that's on a desk or something. That is trigonal planar. Now, since there are 360 degrees in an entire circle, if we divide that 360 by 3, that is where we get the angle of 120 degrees. So this angle here is 120. This angle here is 120, and so is this one. They're all 120. Next question asks, what is the shape of the SO2 molecule? And what would be the angle between its bonds? Go ahead and draw the SO2 molecule's Lewis structure, and then we'll take a look at what it tells us. Between sulfur and oxygen, sulfur clearly has the lower electronegativity. So let's make that the central atom. Now sulfur brings 6 electrons to the table, and so do each of the oxygens. In order to satisfy the octet rule, in order for each of them to be in contact with 8 electrons, we'll need 2 bonds between each sulfur and each oxygen. This leaves us with a lone pair of electrons. And that lone pair is considered an electron domain that would repel other electrons. So this group repels the double bonds. For this reason, this is going to make what's called a bent molecule. It is not given the name trigonal planar because we don't have another atom attached to it. Our central atom is only attached to 2 other atoms, not 3. So the electron geometry is called trigonal planar, but the molecule itself is not called trigonal planar, it'll be called bent. In a bent molecule, the angle is a little bit less than 120 degrees. It could vary depending on several factors. But the idea is that lone pair electrons can actually repel the other groups more strongly than a bonded atom's shared electrons can. So whereas the angle here is 120 degrees, the angle between these 2 bonded groups will be less than 120 degrees. Next question says, what is the shape of a CH4 molecule? And what would be the angle between its bonds? So we know that carbon brings 4 valence electrons to the table. And if those valence electrons want to stay away from each other in 2 dimensions, then we just draw them like this. But our world is not 2-dimensional. It's 3-dimensional. And so if the electrons want to stay away from each other, that turns out not to be the farthest apart that they can get. They can get even farther apart. And we can see this when we look at a pyramid. If we take a pyramid which has a triangular base, and it'll look like this. A pyramid shape turns out to be the shape that allows the electrons to get as far away from each other as possible. So what we'll have is we'll have a carbon in the middle of the pyramid. And if you imagine that its electrons are at the vertices of this pyramid, then that's really the farthest apart that they can get. And so this is going to be the best shape for the CH4 molecule to form. We'll have a hydrogen at each vertex. And we want to show the bonds. We'll have a hydrogen at each vertex. And each hydrogen will bring its own valence electron. All right, now we'll bond these together. And we'll have this. Now we'd like to show that the hydrogen at the bottom here is closer to us in space than the other hydrogens. So one method of doing that is to draw a bond that gets thicker as it gets toward the hydrogen to simulate how the eye perceives things as being closer, as larger. And then we also want to show that this hydrogen could be farther away. So to put that back in space, what people will draw is a dashed line that gets smaller and smaller, implying the pyramid shape. And so the pyramid is looking like this, with the carbon in the middle, and the hydrogen here is closest to us. The hydrogen there is farthest from us. This is an example of what's called tetrahedral. If we look at the NH3 molecule, we'll see a similar kind of thing happen. Nitrogen brings 5 electrons to the table, though. And so what ends up happening is nitrogen can bond to 3 hydrogens and have a lone pair remaining. The 3 hydrogens form the base of a pyramid, and the lone pair will form the top of the pyramid. So we'll have something like this. Now, according to the guide here, what we have is 4 electron domains in both of these molecules. In the one case, the 4th domain is a bonded pair of electrons. But in the case of NH3, the 4th domain is actually a lone pair. In the one case, the molecule will be called tetrahedral, but in the other case, it'll be called trigonal pyramidal. But our central atom is only bonded to 3 other atoms. Now it turns out that geometrically the angle between the bonds is not going to be 120 degrees, it's going to be smaller than that. But it is also bigger than 90 degrees. We had said that the electrons around the carbon would not be in a plane anymore because of the three-dimensional nature of space. They're able to get farther away than this. So if the electrons had been arranged to be above and below the carbon and to the left and right of it, if that was the case, then the bond angle would be 90 degrees. But by taking advantage of the three-dimensional nature of space, the bond angle can be a little bit bigger than 90. And so if we draw a pyramid, we can see that the angle between the bonds would be a little bit bigger than 90. Yes, so this angle here turns out to be about 109.5 degrees. And so when we have the tetrahedral shape, that'll be our bond angle. That'll be the angle between all the different bonds. But when it comes to when we have a lone pair as one of our domains, that can actually repel the other bond groups a little bit more strongly, pushing them closer together with each other. So we'll say that the angle between the bonds here will be a little bit less than 109.5. And this was the trigonal pyramidal shape. Let's take a look at the OF2 molecule. Oxygen brings 6 electrons to the table. Fluorine brings 7. It's worth pointing out that when we decide what shape the molecule takes, it's all based on the bonds that are around the central atom. So lone pairs in the fluorines here will not actually end up mattering when it comes to the shape of the molecule. With this molecule, we see that each fluorine just has to bond once with the oxygen, and then the octet rule is satisfied for all. This means that oxygen is actually going to have 2 lone pairs. When that happens, the lone pairs, they want to stay away from each other, and they want to stay away from the bonds that oxygen has formed with other elements. So let's draw those lone pairs as far away from each other as they can get, and as far away from the fluorine bonds as they can get. We want to go to our table now. We see that we still have 4 electron domains, but this time we have only 2 bonded groups. Lone pairs are not considered bonded groups. These are the 2 lone pairs that we have. So we do have a tetrahedral electron geometry, but our molecule shape will be called bent. The bond angle between them is going to be less than 109.5 degrees, not surprisingly. So this is a bent molecule. The angle we're talking about, of course, is the angle between these bonds. Try to draw a Lewis structure for the water molecule here. A Lewis structure is a great tool, but it is drawn in 2 dimensions. So that's what this section is all about, is trying to see things in 3 dimensions now. Okay, for this molecule, oxygen will be our central atom. The hydrogens bring 1 valence electron. Oxygen brings 6. After we make the necessary bonds, we'll see that H2O, water, has 2 lone pairs. And so this is another example of a bent molecule. In some cases, we may wish to draw the shape of much larger molecules. We may draw some kind of carbohydrate, for example. This molecule is CH3CH2OH. So the way it's written tells you a little bit about the structure. We're going to have a carbon bonded to 3 hydrogens. And of course, that carbon can be bonded to one more thing, so it's going to be bonded to another carbon. That's what this tells us. That carbon has 2 hydrogens that it's bonded to. And then there is an OH. It's a hydroxyl group. And so this is the structure. Now, interestingly, none of the carbons have any lone pairs. All their electrons are bonded. And so if we're asked what type of shape is around the carbon, it's going to be tetrahedral in this case. Why? Because the carbon's bonded to 4 different things. Those bond groups are going to repel each other. So that's tetrahedral. When we look at the other carbon, it is also going to be tetrahedral in shape for the same reason. When it comes to the shape around the oxygen here, though, if we look closely at this situation, oxygen would bring 6 valence electrons, which means that it will have 2 lone pairs. And so this is actually a bent geometry for the oxygen. But that's just the shape around the oxygen. It doesn't apply to other atoms in the carbohydrate. Go ahead and draw the next molecule and see if you can determine the shape around each of the central atoms. Alright, so here's my predicted placement of the atoms, and let's connect them. At this point, we see that the oxygen is satisfied in the orientation that it's in now, and it's satisfied with 1 bond to a carbon and 1 bond to a hydrogen. So with this one, I see that this cannot actually be the solution to this molecule. Even though the oxygen's octet rule is satisfied, I see that the carbon's is not. So there must be some other arrangement of bonds here. So let's try something else. Could it be instead that the carbon is attached to the hydrogen and the oxygen separately here? That works much better. Now the octet rule for oxygen is satisfied, and the octet rule for carbon is satisfied too. So we have a double bond here, and a single bond, and a single bond. So first of all, just like in the previous molecule, the geometry surrounding these carbons is tetrahedral. But when it comes to the geometry here around the carbon, we see that it has 3 electron domains. That is 1, 2, and the double bond makes 3. When we have 3 electron domains and no lone pairs, we're going to have a trigonal planar electron geometry. So that is the answer to this one.